Good morning and welcome to this next lecture on sound and structural vibration. In the last class we reached this point where we were looking at this factor, radiation efficiency. Okay, and we defined it in this manner: the sound radiated by a panel in a certain medium at a certain frequency with a certain amplitude, okay, divided by the sound power radiated by a circular piston in the same medium with the same area as the panel and same mean square space-time averaged velocity. Okay. Now we have been talking about cancellation. So how does this cancellation occur? So we will look at that now. Okay. So I refer you back to the paper by Wallace. Okay. I will give you the title later maybe. So Wallace, in addition to computing radiation efficiencies, numerically, okay, provides at very low frequency analytical expressions for radiation efficiency for various types of P and Q values. Okay. So now let us take P odd and Q also odd. They are odd, that means 1, 3, 5, etc. Odd modes, odd modes, odd modes. Okay. And at low frequencies he gives the expression 32 Ka Kb by P square Q square pi to the power 5. This is the dominant term and there are other terms, smaller terms. Okay. And this turns out to be the maximum value amongst what? The odd modes. That means P is odd, Q is odd. The odd even modes, P is odd, Q is even, or even odd modes, P is even, Q is odd, and finally even modes. Amongst all these modes, this odd mode gives this radiation efficiency which is maximum. Okay. Now this can be, this expression, the dominant term, can be written also as twice K square by pi to the power 5 AB into twice A by P whole squared into twice B by Q whole squared, and if you recognize this, this is twice K square lambda x square lambda z square divided by pi to the power 5 AB. Okay. Now if we compute, if we find the expression okay, of power time averaged power, okay, from a single cell, let me put T for time average, from a single cell, okay, vibrating in the pQth mode. So, the panel is vibrating in the PQ mode and we are looking at one single cell. We compute the power, okay, and we divide by the full area, okay. So, what we get is, we get sigma, okay, let me call it one cell, given by 2 k square lambda x square lambda z square by pi to the power 5 AB. Okay, mind you, these are low frequencies. Okay, these analytical expressions were low frequency, should not forget, low frequency. Okay. Now, if we look at the picture of this thing, okay, if we look at the picture of this thing, okay. So, let us first look at this here. So, the entire panel radiation efficiency at low frequencies is this when P and Q are odd, okay, and the radiation efficiency of a single panel but divided by the whole panel area is this, okay. So, what it means is that the entire panel is equal to one cell, okay. So, how does this happen? So, if we look at this edge, let us say, okay, so now we have this 1, 2, 3, 4, okay, half cycle, half cycle, half cycle, half cycle, and we need one more because it is odd, okay, we need an odd number of half cycles. So, we need this, this makes it odd number of half cycles, okay, 1, 2, 3, 4, 5, 6, this is also not correct. So, we will, let us see, we will add one more. Now, we have odd half cycle in both directions, both are odd, okay. So, now if this region, this positive region cancels with this positive region, this region cancels with that region, and this cancels with this, and this cancels with this, then I have a half of the last cell uncancelled, okay. And similarly, if I look at in the y direction, I mean z direction, these are half cycles, okay. So, this half cycle cancels with this, this with this, this with this, this with this, and so forth. Half here remains uncancelled. So, I have the panel portion here that is uncancelled. Let me put it in red. I have this part here uncancelled, have this part here uncancelled, this part here uncancelled. Okay. So, that is how these 4 quarters amount to one cell. So, that is how your cancellation is happening. Okay. So, now to further elaborate this, okay, so we will just reinforce the idea of coincidence. Okay. So, if we have, let us say, a mode in the panel with a certain structural wavelength, okay, and this is my structural lambda, let us say, okay, and these are the centers of the half cycle, and I am looking at a point here where I am trying to compute my power radiated, and it is very far off, it is very far off. So, that these angles are more or less the same. Okay. These angles, this is the angle, okay, theta, let us say, and these are more or less the same, it is so far off. Okay. Now, so this is pulling down, this is pushing up. Okay. So, there is already a pi difference, phase difference, pi phase difference. Now, what is the path difference? What is the path difference? Okay, to this remote point here, the path difference is this perpendicular distance. This is the path difference. Okay, from, if we collect the volume velocity source to be at the center here and this volume velocity to be at the center here, this is approximately the path difference between the travel to this receiver point. Okay. So, this distance is if this angle is theta, okay, so this angle is theta approximately, okay, and this happens to be my lambda by 2, right, lambda structure by 2. Okay. So, this is lambda structure by 2 cos theta. Okay. So, lambda structure by 2 cos theta is the path difference. This path difference amounts to what phase difference? It is just, okay, multiplied by k, because k, the acoustic wave number, is phase difference for unit distance, right. So, lambda s by 2 cos theta. Okay. Now, if you write k in terms of lambda acoustic, what is it? It is twice pi by lambda acoustic into lambda s by 2 cos theta. So, this 2 goes and I have lambda structure by lambda acoustic into pi cos theta. Okay. This is achieved purely by path difference. This is achieved purely by path difference. There is already a pi difference. Okay. So, this expression lambda s by lambda pi cos theta, okay, or all theta that you can think of, right. So then this will be very close to pi and it will be close to 0 also based on theta values, okay, and it has to be approximately pi. Only then you have this pi added to the pi difference from sine difference. There is a sine difference here, that is the pi difference here. So this pi and this pi added together will give you something like twice pi. That is when you have constructive interference at the receiver. Okay. So in order for that to happen, okay, if lambda s is less than lambda, okay, you will always be less than pi. So this is a schematic, okay. So for a chance of a constructive interference to happen, lambda s has to be greater than lambda. That means structural wavelength has to be greater than acoustic wavelength. Okay. Now we will look at this idea. We will look at this idea from a wave number or frequency domain point of view. The same idea, okay, that lambda x and lambda z have to be greater than lambda for good radiation. Okay, we look at in the frequency domain. Okay, or it's called the wave number domain. So in order to do that, I need one small result which I will derive now here. Okay, a similar idea we have seen before. Okay, so let's see sound radiation from an infinite 1D plate, okay, into a half space. I had used this schematic earlier to demonstrate coincidence, but we will do a little bit more now. Okay, so I have this infinite 1D plate which is carrying a flexural wave. Okay, so what is that description? Let us say eta x comma t. Okay, it has eta tilde e to the power of j, okay, and we will call it omega t minus kp, we will call it kp. Okay. For this case, omega is my choice, we can choose, okay, and we will choose kp also. We will choose the kp also, and this is acoustic half space. Okay. So now if I compute the pressure in the half space due to this panel vibration I will get some amplitude A e to the power of j omega t. Okay, I will get a minus j, I'm sorry, minus kpx, okay, minus square root of k square minus kp square y. Okay, this is the y wave number ky. Ky is happens to be of this form, plus minus square root of k square minus kp square, okay, where k is again my acoustic wave number. Acoustic wave number. Okay, so we'll try to find this A here. That's the idea. Okay, so how to find the A? Now, for harmonic situation, our friend is the Euler equation, which bails us out every time. Okay, so my del P by del Y computed at y equal to 0 is my minus rho del V normal del T, okay, or equal to minus j omega rho 0 Vn. Okay, so what is del P del Y? So del P del Y is, for the moment let's call it minus j ky, okay, A e to the power of j omega t minus kpx. Okay, we are doing it at y equal to 0. Y equal to 0. Okay, that is equal to minus j omega rho 0. Okay, Vn which carries the same wave propagator omega t minus kpx. So both can be cancelled. Okay, so now if I cancel minus and j, A is given by omega rho 0 by ky into Vn. Okay, so now this is equal to a pressure amplitude, this is my velocity. Okay, so if I divide A by Vn, let's say, then I get omega rho 0 by ky, okay, and ky carries a plus minus sign. Okay, so I will put a plus minus here, Okay, now why does ky carry a plus minus sign? If, see, I have chosen kp, okay, and I have chosen omega, so it can happen, let me do it here, it can happen that k is greater than kp, okay, in which case it is going to be a real value for ky will be real value, okay, if ky is a real value, then I would like the sound propagated away in the y direction. So ky must be real and positive. So I have to choose one sign. However, k could be less than kp, in which case ky can be imaginary. Okay. If ky is imaginary, and I have a j over here, and I will have j times something over here. Okay. So I will have e to the power j over here, then a minus, then a plus or minus j times something into y. So j square gives me minus, so I already have j square gives me 1 minus, and this gives me another minus, so I get a plus. Now here, okay, if I choose positive, if I choose the positive sign, this means in the y direction I have a increasing sound pressure till infinity. That can't happen, so I need to choose negative. Okay. So in case of imaginary I have to choose negative, in case of real I have to choose positive. That is the plus minus sign over here for ky. Okay. So now this is pressure, this is velocity, there is a ratio, thus this can be considered a kind of an impedance, we will call it the wave impedance. Okay. So if we change page here, let me write it. So I have the pressure, I will write it as pressure now, okay, and I will write it as velocity, okay, and pressure what, radiated at single wave number, velocity travelling on the plate at this wave number is equal to plus or minus omega rho 0 by square root of k square minus kp square. Okay. So what does it say? So I will replace kp by kx, okay, because of a reason that is coming up. So I will say that pressure radiated at a certain wave number that is moving on a panel divided by velocity at the same wave number that is moving on the panel is equal to plus minus omega rho 0 by square root of k square minus kx square. Okay. So that means what, if I have an infinite panel, I have an infinite panel, there is a wave moving with a certain velocity amplitude, this wave number is kx and the related velocity is vkx. Okay. The related velocity is what, vkx. Then I immediately know, this is the amplitude, okay, then I immediately know the pressure related to that, which is given by pressure related to that wave number is plus minus omega rho 0 by square root of k square minus kx square into v of kx. Okay. So there will be the related propagators, okay, e to the power j omega t etc. on both sides, but this is the amplitude. This is the amplitude. So a single wave number moves on the panel with this velocity amplitude. What is the pressure on the surface? This describes the pressure right on the surface. What is that pressure? That is equal to omega rho 0 with a plus minus sign divided by square root of k square minus kx square. Okay. So this result is important for us. Now what we will do is we will look at the explanation in the wave number domain. For whatever we found so far. Okay, the cancellation effect we spoke of, we will describe or we will try to understand it using the Fourier transform domain. Okay, now we are running out of time, so I will stop here and we will continue from the next lecture.